Okay, today we are going to explain our reading group presentation about long short-term memory. So our team members are Tisum, Ayesh, Tarindu and Dinaka. So this topic is based on a research paper published on 1997 under neural computation. Sepp Hochreiter and Jürgen Schuduber are the authors of this research paper. So let's go with our flow today, and we'll go. So we'll first go through the introductory session, and then we will give a brief introduction about recurrent neural networks, and then previous works, and then we'll explain about the identification of our problem, and then long short-term memory and LSTM's limitations and advantages, and finally we will explain about the contributions which LSTM has done. So first, let's go through the introductory session of this paper. So this paper reviews a problem emphasized by Hochreiter with recurrent neural networks. The problem they emphasize in this research paper is in real-time recurrent learning, the error signals flowing backward in time tend to either blow up or vanish. We will explain about the process in the latter part of the presentation. So the remedy or the solution they will implant into this problem is long short-term memory. A new network architecture in conjunction with an appropriate gradient-based learning algorithm. So let's go through what is recurrent neural network is. Then it will give a brief introductory session for the problem. A recurrent neural network is a type of an artificial neural network which uses sequential data or time series data. So these deep learning algorithms are commonly used, such as in the language translation, natural language processing, speech recognition, and image captioning. So they are incorporated with the most popular applications such as Siri, voice search, and Google Translate. So I will give you a basic structure of the simple RNN network without the bias term. So these are the formulas that we are using in this simple recurrent neural network system, which explains the current state will give as a function of the previous state and the input state as is shown in this figure. So the formula for applying activation function creates a tan h function to uh, diverse with -1 to 1, which includes a weight to the recurrent neuron and a weight to the input neuron. So I will explain the process in the previous in the afterward slides. So the formula for the calculating output, the yt is the output, and there's a weight coming up to the current state, and it will give you the output without the bias term. So let's go to the next slide to the process of this simple RNN network. So a single time step of the input is provided to the network, and then calculate its current state using the set of current input and also the previous state, which comes with a weight. The current ht comes ht minus 1 for the next time step, and one can go as many time steps according to the problem and join the information from all the previous states. So one can calculate the output in each single time step, and once all the time steps are completed, the final current state can be used to calculate the output. So if there is an 10 steps, we are using 9 steps informations to calculate the 10th step. So the output is then compared to the actual output, the target output, and the error is generated. The error is backpropagated to the network. We will explain in the latter part of the presentation to the network to update the weights, and hence the network is trained. So let's go to the next slide. So I will explain about the principle of the backpropagation. Backpropagation is when desired output pattern exists. If each function is differentiable, we can use a backpropagation network. So as if with conventional gradient descent or ascent, backpropagation works by for each modifiable weight calculating the gradient of a cost or a error function with respect to the weight and adjusting it accordingly. So in a simple recurrent neural network, as we talked previously, has an activation feedback which embodies with short-term memory. So a state layer is updated not only with the external input of the network, but also with the activation of the previous, which we call as a forward propagation. So what is propagation means? It's a feedback which modifies the set of weights, and it enables automatic adaptation through learning. So we'll go to the next slide. So backpropagation through time is can be explained by these functions. As we know, the current state is a function of the input state and the previous state, and it was added by a weight of the hidden layer. And the output state can be given by a function which includes the current state and the weight of an output layer. So it gives a simple figure. It can be shown in a single figure like this. So how we calculate the total loss all with all the time steps? So the total loss can be calculated by each and every loss function in each and every step, and by getting the sum of each and every loss function in each and every step and divided it by the total time will give the total loss across all the time steps. Let's go to the next slide, and this will explain about the backpropagation process. So the gradient can be get by da by L over da by WH, and it as we explained earlier, it will divided by the time and it will divided by the da by WH, and then we applying the chain rule for this function, and da by OT will added to the two sides and dab ht to the two side, and the chain rule after applying the chain rule, it gives that ht depends on both ht minus 1, which is the previous state, and the wh, which is the weight, and where computation of ht minus 1 also depend on the weight. So the chain rule can be yield to dab ht over dab wh to these two terms. And by assuming these terms as AT, BT, and CT, we are getting a simplified equation as the finally WHT over WH, and these are the terms which will be long whenever the T is large. So the next part will be explained by Dinelka as previous works.
In previous work, they mainly focused on the recurrent nets with time-varying inputs. Gradient descent variance is the approaches of Elman, Fullman, Williams, Stmude, Perlmutter, and many of the related algorithms in Perlmutter's comprehensive overview suffers from the same problem as backpropagation through time and real-time recurrent learning. Time delays discovered by the Lang et al. Plate and Dewey's and Principi, and this is practical for short time lags only. Time constants discovered by Moser, Dewey's, Principi's, Sun et al.'s alternative approach, and this deals with long time lags. The net input tends to perturb and stored information, which makes long-term short impractical. Ring's approach is proposed by Ring in 1993, and he proposed a method for bridging long-time lags, and this approach can sometimes be extremely fast. Uh, Benjo et al.'s approach was proposed in 1994 to investigate methods such as simulating annealing, multi-grid random search, time-weighted pseudo-Newton optimization, and discrete error propagation. Kalman filters were used. Pushkorius and Feldkamp in 1994 used this technique to improve recurrent net performance. Not useful for, but this is not useful for very long minimal time lags. Second order nuts were proposed by Watrous and Kuhn, and in here use multiplicative units, and they this architecture does not enforce constant error flow, and it's not designed to solve long time lag problems, and it has fully connected second order sigma phi units, while the LSTM architectures multiple units are used only to get access to constant error flow. Simple weight guessing is discovered by these persons to avoid long time lag problems of gradient based approaches. They simply randomly initialize all network weights until the resulting net happens to classify all training sequences correctly. Weight guessing is a good algorithm for the problems that are very simple. More realistic tasks require either many pre-parameters or high weight precision, such that guessing becomes completely infeasible. Adaptive sequence chunkers was discovered Himuduber and Moser and do have a capability to bridge arbitrary time lags, but only if there is local predictability across the subsequences causing the time lags. The performance of chunker system, however, deteriorates as the noise level increases and the input sequences become less compressible.
Kian.
As for the problem identification, which focus on the exponentially decaying error, this slide here, which directly taken from the LSTM Neural Computation Research Paper, page 3, shows the main function of output and hidden layers of a simple recurrent neural network, which we will use on the next slide to explain the problem regarding simple recurrent neural networks. Let's move on to the next slide. Uh, as for the outline of Hochreiter's analysis, he have derived the gradient descendant function using these terms. Uh, as for the term we see here with the chain rule, determines the total error backflow. Uh, mm, let, to understand the problem, consider this function, which include the previous mentioned term. As for the exponentially gradient, if this term is greater than 1 for all m, then the largest product increases exponentially with q. That is the error blow up and conflicting error signals arriving at a unit v can lead to oscillating weights and unstable learning. Gradient flipping can be identified as a solution for this problem. If this term is less than 1 mm, uh, for all m, then the largest product decreases exponentially with q. That is, the error vanishes and nothing can be learned in acceptable time. Mm, from this point forward, Jisum will explain the. Jisum will continue the presentation.
Thank you, Dinilka. Uh, as you can understand, the main problem regarding vendor recurrent neural networks architecture is the vanishing of error component in long-term basis. So here we discuss the remedy proposed by the authors of this paper called long short-term memory. And also in this presentation, we are not going to explain the mathematical background because of its complexity, but give an elaboration of how this architecture works. So as I mentioned earlier, since the problem is vanishing and exploding error components, they proposed of this constructed architecture is to allow a constant error flow through special self-connected units. This LSTM architecture shown in the slide consists of these main functionalities: input to the LSTM, hidden state, cell state, forget gate, input gate, uh, output of the LSTM, and weight and biases. Basically, a single LSTM cell has 4 different components: forget gate, input gate, output gate, and the cell state. We will first discuss the use of these parts in brief. In the forget gate, as the name suggests, this part is responsible for deciding what information is to be thrown away or kept away from the last step. This is done by the first sigmoid layer. Based on previous in state and the current input state at time step t, this decides a value between 0 and 1, which for each value in this cell state. For all ones, all the information is kept. As it is for all zeros, all the information is discarded, and with other values, it is decided how much information from previous state is to be carried to the next state. the input gate. The next step is to decide what new informations we are going to store in the cell state. This has two parts. First, a sigmoid layer called input gate layer decides which values we will update. Next, a tanh uh, layer creates a vector of these candidate values that could be added to the state. In the next step, we will combine these two to create an update to the state. Then these two values combine to decide what new input is to be fed to the cell state. The cell state serves as the memory of an LSTM. This is where they perform way better than vanilla RNNs when dealing with longer sequence of input. At each time step, the previous cell state combines with the forget gate to decide what information is to be carried forward, which in turn combines with the input gate to form the new cell state and or to new memory of the cell. At last, the LSTM cell has to give some output. The cell state obtained from above is passed through hyperbolic function called tanh, so that the cell state values are filtered between minus and 1. This is the LSTM cell given in the research paper, and to understand the functionality, let's discuss these following terms. As for network topology, they have used networks with one input layer, one hidden layer, and one output layer. The fully self-connected hidden layer contains memory cells and corresponding gate units. The hidden layer may also contain conventional hidden units, providing inputs to gate units and memory cell blocks. S memory is memory cells sharing the same input gate and same output gate from a structure called memory cell block of sizes. Memory cell blocks facilitate information storage. As with conventional neural nets, it is not easy to code a distributed new input within a single cell. Since each memory cell block has as many gate units as a single memory cell, the block architecture can be even slightly more efficient. As for the learning, they have used a variant of real-time recurrent learning properly takes into account the altered multiplicative dynamics caused by input and output gates. However, to ensure non-decaying error backprop through internal states of memory cells, as with truncated backpropagation through time, errors arriving at memory cell net inputs do not get propagated back further in time, only within memory cells. Errors are propagated back through previous internal states. Tarindu will continue from this over.
Thank you, Disham. When we're talking about limitation of LSTM, the particularly efficiently truncated backdrop version of the LSTM algorithm will not easily solve problems similar to strongly delayed XOR problems, where the goal is to compute XOR of two widely separated input that previously occurred somewhere in noisy sequence. And also, each memory cell block needs two additional units. In comparison to standard recurrent nets, however, this does not increase the number of weights by more than factor of 9. Each conventional hidden units replaced by at most 3 units in the LSTM architecture. Generally speaking, due to its constant error flow through CECs within memory cells, LSTM runs into problems similar to those feed-forward nets seen the entire input streaming at once. Actually, LSTM does not have any problem with notation recency that go beyond those of other approaches. All gradient-based approaches just, however, suffer from practical inability to precisely count discrete time steps. Advantages of LSTM: the constant error backpropagation within memory cells result in LSTM ability to bridge very long time lags. And also, for long time lag problems such as those discussed in this paper, LSTM can handle noise, distributed representations, and continuous values. Actually, LSTM is the best method for the problems previously discussed. Other advantages of LSTM, there appears to be no need for parameter fine-tuning. The LSTM algorithms update complexity per wait and time step, essentially that propagation through time. This is excellent in comparison to other approaches such as real-time recurrent learning. Unlike full propagation through time, however, LSTM is local in both space and time. These are the contribution for LSTM. Yeah, in 2009, an LSTM based model won the AGDAR Connected Handwriting Recognition Competition. In 2013, LSTM network were a major component of a network that achieved a record 17.7% phonom error rate on the classic TIMIT natural speech dataset. In 2014, a simplified variant called graded recurrent unit was introduced. In 2015, Google started using an LSTM for speech recognition on Google Voice. According to the official blog post, the new model cut transcription errors by 49%. In 2016, LSTM has biggest contribution in these areas. Google started using an LSTM to suggest messages in the Allo Conversation app. In same year, Google released Google Neural Machine Translation System for Google Translate, which use LSTMs to reduce translation error by 16%. Apple announced in its worldwide developers conference that it would start using the LSTM for quick type in iPhone and for Siri. Amazon released Polly, which generates voice and behind Alexa using a bidirectional LSTM for the text-to-speech technology. These are references that we use to prepare the presentation. Thank you for listening.